I say just one word, Jeroje, and then it's finished. Oh, Nangadet as well, of course. So I tend to move a lot when I give presentations. I hope it's okay because I get very excited about things. I hope this is okay. Yeah. That's. Huh? Oh no, because then I move I fall. Can we see it? I mean, perhaps too much light. No? But if I stand here, probably you don't see the screen, right? Perhaps on that side, right? On this side, okay. Like this probably is better, right? Yes. Before starting your presentation, yes. Yes, very good. Yeah. So I just stay here on the side. Yeah. Okay, dear colleagues, dear Agostino, welcome here at the University of Amadou. So you are the first student, we have the first presentation in this university, and is a series of scientific conference that we have organized in university, and we have an approach, multidisciplinary approach to research. And, your presentation is the first one for us. And welcome you. You have the floor. Thank you. Thank you, Professor Faye. Thank you for the for inviting me, for giving me the opportunity to be here, and it is an honor, a privilege to be the first one giving a seminar in this institution, and at the same time a great responsibility. You know, I mean, hopefully everything. And thank you also, you know, for the kind invitation, for the kind words. I hope this is just the beginning of a very long, successful cooperation together. All right, so let's go directly into the presentation. I actually have two prologues. So before even we start to introduce my scientific topic, the topic I'd like to present you today. The first one is just to give you a few words about the place where I come from, the institutions where I come from, so that we can get to know each other a bit better. So I work in Bremen, and in Bremen there are two academic institutions, two universities. One is the University of Bremen, and the other is Constructor University. The University of Bremen is a public university, and Constructor University is a private university, and I am affiliated with Constructor University. Okay, so I'm a professor there at Constructor University, but I work, my everyday research is done at the Leibniz Center for Tropical Marine Research. This is where I do my research, this is where I have my group. So this institute was funded in 1991 and joined the Leibniz Association, which is one of the four major research associations we have in Germany, joined that association in 2009. We have nowadays approximately 200 employees, including scientific staff and administration staff and technicians, and we have 8 joint professorships with the universities I just presented you. So we have 20 research groups, and one of my group is part of this community, and we have 700 alumni around the world. The mission of our institute is to work in the tropics with people from the tropics. That's the mission. And the institute is structured into 4 major departments: biochemistry and geology, ecology, integrated modeling, where I am, and social sciences. So it's a very multidisciplinary working environment, and we work multidisciplinary in various, in 5 major research areas, dealing with resources, managing resources, global change, climate, global environmental problems, and so on, and various other topics. Just to give you an idea about the PhD community, I'm not sure if you can see, but more than 50% of the PhD students in our institute come from tropical countries. More than 50%. German students are only 30%, and the rest, approximately 17, are from the rest of Europe and US and so on. So the big community comes from tropical, subtropical countries. We are very pleased that more than 50% are female students, and in the other pie chart, you can see that scholarship or third-party funding PhD positions are approximately 40%, and 60% are PhD positions that are financed by core funding by our institute. Okay, and this is the last overview I want to give you for the first prologue. This map gives you an idea about the area where we work, and the black dots represent projects that have been completed, and the blue dots are the projects that are still currently ongoing. As you can see, West Africa and Sub-Saharan Africa is a hotspot for us as a research location and partnership. All right, so that's the first prologue about where I come from. Second one is more towards the science I'd like to present you today. So, one of the questions I've been thinking is, what is human's secret of success? If we can call success what we are doing at our environment. I think you know what I mean. How we come to dominate among all the species on this planet, how we come to dominate the environment, okay? Only 60,000, 70,000 years ago, We were an insignificant species among many others. Actually, there were other species that were more dominant than us. What happened in these 60,000 years? What made us reaching the stage we reached, dominating the rest, this planet? Okay, so it's not just me, of course, that was playing with these ideas. There are anthropologists, historians, ecologists, and paleontologists, all trying to look at this. And there are some general answers. There are some aspects that can give us some ideas. The characteristic of humans is that we are social animals. And there are other social animals on our planet. But insects are one of those. What is their characteristic, the society? What is the sociality of these animals? How can we characterize that sociality? Well, these insects, they can cooperate in incredibly large numbers. Think about bees. And, but very inflexibly. They do always the same thing. Very inflexible. Think about termites. I mean, amazing, you know, one of the reasons I love to come to Senegal is to see these termites, amazing social animals. They can engineer their beautiful house to air condition it perfectly, you know, socially extremely well. But big numbers, but inflexibly. Always the same thing, rigidly. On the other hand, huge numbers, inflexible. On the other hand, there are other type of animals. For example, this is an example that they can cooperate more flexibly, very flexibly. They show all sorts of cooperation behaviors, but interestingly in small numbers. The group, you know, where there is an alpha male, you know, it can reach 60, 70 individuals. It can't grow anymore. If it keeps growing, then it falls apart, and two groups emerges from there. Okay, so very flexible cooperation, but in small numbers. Okay, perhaps it's clear where I'm going. Then it's us. We can cooperate extremely flexibly and in extremely large numbers. Think about a nation. What is a nation but many, many individuals, millions of individuals, somehow cooperating, directly or indirectly, right, for a common purpose, right? There is some social identity involved, and so on and so forth, right? So that's the thing about us. Cooperate very flexibly in large numbers. Now, the question is, how do we understand this? So how do we understand human behavior in the environment? If we have to, you know, tackle such complexity, many people doing many different things, many different range of behaviors, okay? How do we do that? And that's the topic of my scientific presentation. So, hey, finally, we got to the introduction. Are you familiar with the concept of common pool resource? A common pool resource is a type of good that which has the characteristic of being big, very large, and is very difficult from preventing people from gaining or from obtaining benefits from this good. This good could be natural. Think about a pasture land. That's a common pool resource. Think about a fishery ground, a common pool resource, or a forest. Okay, it's large. That's the main characteristic. It's difficult from preventing people, but although not impossible, very difficult, but not impossible, from preventing people from obtaining benefits, from extracting. That's why it's called common pool resource. Okay, it's difficult, but not impossible. Think about a fishing ground. Of course, we try to regulate it, we try to monitor it, but think about all the illegal fishing that is going on anyway. It's very costly to monitor, you know, to the level of preventing, you know, individuals from, you know, diverging from governance rules and so on and so forth. So that's the characteristic of a common pool resource. The problem about common pool resources is that they are overcrowded, they are overused, they are polluted, and they are even destructed completely. And we have experienced already several tragedies of the commons situation. That concept means that a common pool resource can be used by anybody. Every individual try to maximize the benefits extracting from that resource, but the consequences, if the resource collapse, are felt collectively by everybody. And that's a tragedy of the common. It's a term, it's a concept that was coined by Hardin in the 60s, in the late 60s. We have experienced already many of these tragedies of the common situations. The problem is that there are, again, as we were thinking with this general concept about human characteristics, there is a wide range of extractions, of harvesting from these common pool resources, a wide variety of behaviors. Okay, and basically the interest of my own interest, but I mean, surely many of you, is to understand under which conditions a common pool resource can be managed sustainably in terms of, in ecological terms, but also in socioeconomic terms. Let's not forget that resources are critical for human well-being. Okay, so somehow we need to use resources. Okay, that's an example of a tragedy of the common. It's a classic example. It now features in every ecology book about fishery science. It's the collapse of the North Atlantic cod fishery. Okay, this fishery sustained thousands and thousands of people for centuries. Okay, until it collapsed in the mid-90s. When it collapsed, thousands of people lost their job. The population of Newfoundland dropped by 10%, and unemployment rose to almost 20%. And this plot shows you how many stakes, how many individual stakes were involved in that fishery, how many countries, a huge number of stakeholders, all invested heavily into infrastructure, into boats, into fishing technology and so on, right? And they all felt very strongly that there should be an open access policy to that fishery, okay? But of course, what is in the interest of individuals is not always in the interest of the community as a whole. And therefore, the ecosystem was brought past its sustainability threshold and collapsed, leaving everyone worse off, okay? But there are also good stories. One good story is the main lobster fishery, which landings and economic revenue have been increasing steadily over the past 3 decades, to the point that, approximately 10 years ago, the fishery got the Marine Stewardship Certificate, which is a certificate given by an NGO based in London for sustainable practice. Okay? But somebody think that is not, this successful story is not only to do with good management or sustainable management, sustainable use. Somebody think that perhaps it's the warming trend that was conducive to lobsters, juvenile lobsters, to survive longer. Or perhaps the demersal fish, the fish that lives at the bottom of the sea, that, with increasing temperature or for whatever the reasons, started to decline. And since these are the main predators of juvenile lobsters, then the lobster benefited from the situation. So basically, what I'm trying to say is that we are dealing with a complex system. On one side, people, users, resource users, right, respond and have an impact on resources. On the other side, the characteristic of the resources have an impact on people behavior. And the way the resource, develop has an impact on people behavior. So basically, users or, those who benefit from that resource tends to maximize current harvest. Everybody wants to get as much as possible. The resource productivity, therefore, and future payoffs, the future gains that you might get from that resource, therefore decline with declining resource level. People, users, those who extract from that resource, discount their future payoff, their future gain. They discount, they ignore it, they give them up. They want to get it now, based on their current expectations, of course. And basically, this is a complex adaptive system characterized by nonlinearities and regime shifts. Okay, I really want to focus your attention on discount, this concept. This is a fundamental concept in economics. Okay, we discount our future. We discount the future of others. Different people discount their future at different rates. Okay, so that is a very fundamental concept in economics. So it is to do with the fact that, if I want to offer you a sum now, to be able to offer you and make it attractive, that sum of money at this point in the future, I have to increase that sum of money. Because otherwise you will discount it. Okay, and that increase, the rate of increase, is the discount rate. Okay, so that's a fundamental concept. So now the question is, how can we address this complexity? How can we address these problems that I've just outlined? Well, I'm a physicist, so by background. So to me, an approach that holds some promises is what we can call the macroscopic approach, precisely like in classic thermodynamics. In classic thermodynamics, you work with measurable, observable properties, pressure, volume, temperature, right? You don't care too much about how each single molecule is, what is each single molecule is doing. All the many thousands and millions of molecules composing your system, right? You look at the macroscopic properties. So, in a similar way, I wonder if there is some sort of property, macroscopic property, with which we can characterize the resource user system, and with which we can describe the resource user system without losing, important information. Yes.
Yeah, we need to share your.
Yes, we can do that. Shall we do a break? Yeah. Do we want to take now a break? We can do it now. Not now? No. Yes, let's do it. Yeah, no problem. So, how do you want to share it? Or otherwise, we can put the presentation on that computer. Yeah. Okay. Wait. I need the connector. Yeah, I do. Coming. Whoever is. People online cannot see the slides? Okay. But I can share the slides later, or oh, sorry about that. But they cannot see with the camera the slides? They should be able to see the slides through the camera, right? So, ah. But why they don't point the camera at the slides and then they can see the slides? It does not need to point me. I mean, I'm not a good thing to look at. You know, the slides are more interesting. The camera, yes, yeah, of course. Yeah, but better than not. We continue?
I think we continue.
Okay, that's no problem. Yeah, no problem. Yeah, yeah. You can keep the camera there, and it's better than nothing, right? Even if it is not very visible, it's better than nothing. Okay, so we got to that point. And by the way, this approach that I have in mind is I can't claim is new. It's actually well developed, this idea, at least from a mathematical modeling perspective. There are several articles where this was developed like in the 90s and the 2000s, and most of what I will present, the results I will present, are inspired by the work that is there, and especially by the work of Simon Levin. Okay, so what is this property? Well, in ecology, there is this word that is called traits. Okay, that is a characteristic. What is a trait? A trait is an observable or measurable characteristic of an individual organism. Okay, it could be morphological, it could be physiological, it could be of any type. It's observable, it's measurable, and that is inherited or environmentally determined or both. That is a trait, a characteristic. Okay, so in our ecological, in our user resource system, what could be a trait that can allow us to capture human behavior? Well, more generally, remember my prologue number 2, cooperation, human cooperation, the way humans cooperate, the degree to which they cooperate or they do not cooperate. Or more specifically for our case, because we are looking at a resource, is harvest behavior. How do we harvest from that resource? Okay, that's a trait. The idea is to take this property, this trait, harvest behavior, and see how that trait can tell us or can describe the user resource community as a single adaptive entity. Okay? But there is a key aspect, which is that a trait, like any trait, a trait is a skill. It's so basically, yes, basically in nature, skills, you cannot maximize all skills, right? So because resources, energy is limited. So if you invest in that skill, you have less to invest in these other skills, right? A little bit like when you think about the Olympics, right? There are those who are 100 meters fast runners, they have certain skills, but they cannot compete, for example, with marathon people because they have other skills, right? So you cannot maximize all because resources, energy is limited. So there are trade-offs. And so we need to think about the trade-offs connected to harvest behavior. The trade-off is actually fairly simple and hopefully quite naturally now, because we've been discussing about that. If you harvest everything now, you have less for the future, right? That's something, some sort of trade-off connected to harvest behavior, and therefore to discounting. How do we discount our resource now with respect to the future? So this is just a schematic to tell you the mechanisms in a very intuitive way. Think about a renewable resource, like a fishery, right? Can renew itself over time.
subject to logistic growth, right? There is a carrying capacity and maximum growth rate. And think that the blue bar would represent the size of the resource at the time that we call present. Okay, so if I harvest aggressively, then I try to take as much as possible of that resource now, which means that at some point in the future, the resource might not be able to renew itself at the same rate at which I'm harvesting, and so in the future I get much less. Okay, so that's one situation. So that's low discount factor. I'm zero. I'm discounting the future. I consider my future zero. Okay, low discount factor. The other case is when, okay, I try not to take too much now and leave something for the future. So I may expect that the resource might grow to some level, and in the future I can still get some of that resource. Okay. So in this situation, you can think of that part, right? Perhaps you cannot read it. That part of being the cost for being more cooperative, right? Because in the first case, you're not very cooperative. You don't care about the others. You're trying to get as much as possible now. You're not very cooperative. In the other case, you are more cooperative. Okay? So that is the cost for being more cooperative, because you're not getting that amount now. Okay? And if you want the other part for the future, that is the profit you have for having being cooperative. Okay? So basically, you can think of this like the low cooperation case, right? The low discount factor, when I don't care about my future, I'm not very cooperative with others. And that is the high cooperation case, okay? So this is harvest behavior, being aggressive or, being a bit more moderate, and the trade-offs involved, okay? Good, we have the concept, we have everything. Let's look at this model, how might come together. In fact, the model is fairly simple. There are only two equations. And that's my aim, my original aim. I don't want to have millions of equations, everyone representing. Think about Mbour, one of the biggest fishery landing location in Senegal, right? You know how many pirogues there are there? 20,000. Not all at the same time at sea, but that's the size of the fishery, 20,000. So if you want to see every single agent, every single pirogue made of, I don't know how many fishermen on a pirogue, right? If you want to model that and want to look at how many they are catching and how much of the fish lands and so on, I mean, you end up with a model that is fairly heavy in terms of number of differential equations. Here, only two. First one, the temporal dynamics of the resource. It's just the difference between two terms. The first term is the resource growth rate. Okay? The resource growth rate is logistic. It grows, the resource grows according to the carrying capacity, so very simple. And the second term is how much you extract. C stands for consumers or users. Sorry for mixing up terminology, but it's the same thing. The consumers or the user, those who extract, the fishermen, okay, which ultimately us that love that fish on our table, right? So that's the extraction, the rate at which we harvest, okay, that minus. That follows a monod type of function. It's simply basically a saturating function, okay? I just want to point your attention to the parameter Ks. That's called half saturation constant. That's the level of the resource at which harvest is half the maximum. That's why it's called half saturation state. Okay, half the maximum. Now you see there in this example I'm providing is that when that half saturation constant, when K is small, harvest is very aggressive, very quick. The red line. When K is large, then harvest is low and moderate. Yeah, the blue line. So K. When K is small, harvest is aggressive, fast. When K is large, harvest is moderate. That's important because the harvest behavior will be hidden in that K. That K is not going to be a constant like in many models. It's going to be a variable over time. Okay? So to keep things simple, the consumers or the users or the fishermen is kept constant. The point is we want to see how the trait harvest behavior evolves over time. So that's what we want to capture. By capturing how harvest behavior evolves over time, we hope to capture the user resource system as a whole in some way. Yeah? So that's the equation, the temporal dynamics of the trait. The temporal dynamic of the trait follows a so-called canonical equation of adaptive dynamics. Okay, it's an adaptive. The trait is going to adapt over time. It's an adaptive process. Any type of adaptation, whether environmental, whether developmental, whether evolutionary, is such that the trait evolves towards values that maximize the fitness of the system. Okay, and that is precisely described by this equation. The variation over time of the trait is proportional to the gradient of the fitness function. Okay, with a proportionality, with a constant of proportionality, which reflects the speed of the adaptive process. How fast the trait is adapting towards values that maximize the fitness of the system. The fitness of the system is F, which is basically the sum of two terms. What you harvest now, and what you forego, and what you give up, or you leave for your future, or what you give up. That's the second term, okay? So, of course, that's the current harvest, which is the harvest rate that was on top in the equations for the resource, okay? And the Ka, the observation constant, depends on the trait. When the trait is 0 there, I don't know if you can see, but when the trait is 0, then the Ks is smallest. It means that it's very rapid, the harvest. So when the trait is small, it means very aggressive. When X is small, it means harvest behavior is very aggressive. When X is different than 0, the K is large and is more moderate. Okay? That's the harvest behavior in there. It's not only in their harvest behavior, because the discounted resource, what you give up for the future, okay, is composed of several factors. One term is the per capita productivity of the resource based on the current level of the resource. That's basically what you expect you might get in the future. And then the discount factor. The discount factor is the product between the parameter omega max and the term that depends on the trait, but that could be either 1 at most or smaller than 1. Because when the trait is 0, it means you harvest very aggressively. That is 1 minus 1, it's 0. When you harvest very aggressively, you don't have the future. That is the future, what you leave for your future. You get everything now, the green part. Okay. When X is large, E to the power of minus X is 0, so that is 1. And basically, omega, the maximum discount factor, is determining how much you want to leave for your future. That omega max is very important. That is the upper limit. Since the thing in parentheses goes from 1 to 0, the upper limit of what you leave for your future is determined by that omega max. It's called discount factor, very important in economics. Economists have complex model for that omega max. Here in our simple model, that is going to be just a parameter. And we are going to change the value of that omega max to see what are the effects on the user resource system. But otherwise, that could be very complicated. What is that upper limit? Well, that is the rule of the game, for example. That is the governance system. How secure is our user resource system? How, how certain we can be that it's legally and that all the players are abiding by the rules and so on, okay? So if that is small, well, governance has some problems there, yeah? And so on and so forth. And it can be a very complex function because things, governance, rules, players, people can come in, illegals, all of a sudden without you being able to control and so on, right? Unfortunately, things that happen in this, for Senegal, which is a very problem for the Senegalese economy. When you see the conflicts emerging from the artisanal fishery in the country and industrial fishery coming from outside. Okay, so anyway, okay, so that's omega. Good. So I just wanted to give you an intuitive understanding of this, how this fitness function looks like. Because this fitness function is, if you're familiar with evolutionary ecology, it's a thing like, like mountains and valleys and so on. And the mountains is the place where the fitness is higher of this system, right? And the trait always wants to go, because this is like an optimization problem in mathematics, right? The trait always wants to go where the fitness is, where there's a local maxima in the fitness function, right? Okay, so here I'm showing you three fitness landscape obtained with three different values of omega. The first value I need to is very small omega, it's 0.5. I don't think you can see it. I cannot even see myself, but the first one is over here, is very small omega, so very little future that you think. The second one is intermediate. The third one is very high. This one where you see this very deep red. Okay, and basically this fitness function is here determined by harvest behavior on the x-axis. So is this x, how aggressive or how moderate you are in harvesting. Small numbers here is very aggressive. High numbers here is very moderate. And then the resource level, okay? So basically this black line tells you that at every resource level, what is the trait value that maximizes fitness. This black line is the value of maximum fitness in this landscape. When omega is small, the flexibility you have with your harvest behavior is very small. See how it is here? Very little flexibility you have. When omega is high, like in this case, you have a huge flexibility. You can have many possibilities in the way you harvest. Omega high means a very well certain system, nicely regulated, lots of money invested in monitoring and so on and so forth, okay? Social security for all the players and so on and so forth, okay? That's the case. And there's lots of flexibility in that case. A huge range of harvest behavior. Fitness is maximum all along. Okay, and another aspect I want to draw your attention to is that when the resource is low or very high, people don't see the need for being moderate. People harvest a lot. When the resource is low, of course, I mean, it's going. I need to get as much as I can. It's going, tomorrow I won't get anything. When the resource is plenty, who cares? I can get whatever I want. People is moderate when resource levels are intermediate. Oh, sorry. Are intermediate. It's a very interesting thing. We were quite amazed about it to see such a very neat aspect about our very simple little nitty-gritty model. And we started to look at literature to see whether this is reasonable, if this exists. And we were amazed to discover that, I'm not sure if you are familiar with Elinor Ostrom. He was a Nobel laureate in economics, probably one of the most famous figures of resource economics and environmental economics. She wrote a review paper in Science. She was an observational economist. She has been observing for decades user resource system of all types, fishery, forestry, all around the world. And she wrote this amazing review about all what she understood from observing real resource system. And she said, a resource's current productivity is a curvilinear effect on the self-organization across all sectors, fishery, forestry, whatever, pasture land. If a fishery is exhausted, or it is apparently very abundant, users will not see a need to manage for the future. I mean, basically our model contains that mechanism, simply based on this trade-off, very simple. Somehow the model contains that mechanism. It's not prescribed. It's an emerging property of the model. We were quite amazed. Okay, with this in mind, we were quite happy, and we said, okay, now let's run this model. Let's see what happens, some real situation. So what we did here, you see that random walk there? That's the maximum resource growth rate, okay? The growth rate, because think about, cannot be a straight line, right? The resource does not always grow at the same constant rate. Why? Because climate is changing, because today is raining, tomorrow is not raining, and we are exhausting the soil, and so on and so forth. All different things, right? So it's a random walk, in fact. It's a random walk around an average. The average is 0.01, because that's what happens, right? The growth rate is a trait, is a characteristic of an organism, right? It goes around a certain fixed value, but because of variations in life, it can fluctuate, right? It's a random walk around a fixed mean. So we force the model with that random walk, with that growth rate, and we see what happens. And we have three cases. First case, when omega is 0, it means the system is crazy. Just people just go there and harvest and don't care about anything. They don't care about the future. They don't care about the social, the organizational, the rules, anything. Omega is 0. When omega is 0, everything collapses immediately. Even if there is a little increase here, right, in the resource growth rate at the very beginning, everything collapses very rapidly. Why? Because X, the harvest rate, moves towards very aggressive harvest, because there is no future. The second term in that equation is not there. Everything is the first term, harvest now. Everything collapses. So the total harvest over the simulation time is very small. Intermediate omega. Intermediate omega. Well, it's better. It's better. The harvest rate, sorry, is stable for a while. Okay? The resource grows even for a little while, up to a point when the growth rate starts to go really, really down here. The growth rate starts to go really, really down. When that happens, the dashed line here is the future productivity. And the continuous line is current harvest. It flips, basically. When the resource growth rate goes down, 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 the harvest behavior goes low because everybody wants to harvest aggressively. And so these two terms revert and the system collapses. The overall gain is a bit higher than before, but still fairly little. What if we have a very big omega? I think you got the point now, right? So everything stays kind of flexible. When there is this dip here in the resource growth rate, people will harvest less. There is flexibility. So the harvest rate goes high, people harvest less. And then when the resource is plentiful, people can harvest even more aggressively. The trait become more aggressive and so on, right? There is space for flexibility when omega, when society, the rules of the game, regulations and everything is secure. There is certainty for the future. If there is certainty for the future, okay, I know that, my friend here is not grabbing everything he can. I know he's obeying also to the rules. Then I can relax. I can get a little bit. He can get a little bit. We can all be nice and cooperative. And that's what we get. In the end, everybody is better off because it's a renewable resource. The resource can renew itself. We can get as much as we want if we do it properly. That's the main idea. Okay, but this is just one. Right? This is just one case. What we did, we ran hundreds of thousands of these simulations with this random walk, always the same mean. All these very different random walks are around the same mean, at the same mean, but the fluctuations change from no fluctuations, so a random walk that just moves along the mean, so very stable, to extremely high fluctuations. Okay, huge variance. Okay, we did that, and here I'm presenting all the results. Okay, so at the bottom, and also over a continuum of omegas, over a continuum of discount factors. Okay, so 0 on the x-axis is the discount factor, omega. 0 means no future. Very high means very secure social system, very secure economic system. Okay, and the variance over there, the variance of the fluctuation in the resource. So at the bottom on the y-axis is low variance, so resource growth rate fairly stable, and extremely unstable on the top, which means, for example, climate change. With climate change, we expect that the frequency of changes in resources will be much higher. So if you like, on the top is more like what we would expect in the future in terms of ecological fluctuations in our resources, okay? So very clearly, we have two regions, the sustainable regions where things go well and the collapse region, separated by a very sharp cliff. Okay, that's the region where everything collapses. Okay, when omega becomes small, when the social system is less secure, things collapse. But the amazing thing is that that cliff separating the two regions is not a straight horizontal line, it's obliquous. It means that with increasing climate change, with increasing fluctuation in the resources, your omega has to be higher to allow for more flexibility. You know, this is the direction we are going. With climate change in the future, our institutions have to be more solid, more secure, more better regulated. That's the take-home message of this very simple, you know, very simple model. It's, as you notice, it's a little bit incredibly valid. And the reasons I picked up this topic to present you today is because it's at the base of all my science. Most of the research I do is based on this concept, on these approaches, evolution, in order to get some meaningful insight. Okay, like harvest behavior. Modeling tools for studying the evolution of social ecological systems can be developed. These modeling tools can be applied to any community, large, no matter how large. Who cares? It could be millions of individuals. Any community of competing entities for which we can define an appropriate trait and the constraints of that trait, the trade-off. Higher resource variabilities, that's the result. The more higher the resources fluctuating a lot because of climate change, higher uncertainties, then you require a more robust and reliable social and governance system. And I would like to thank the people who contributed one way or another to this work. Gunnar Brandt, Björn Forland, Michaela Kulesh, and Hakim Schluter. Thank you very much. And I'm happy to take questions. Thank you. The climate change physics. Go for it. People here call you? Sorry. No. Ah, okay. Yep.
Thank you. Thanks for this
Thank you.
and it's nice to see that you guys use the microscopic approach
Yeah.
in complex system. So my question is, so the omega, for example, we give some value of omega.
Yeah.
So if you want to extend this model, for example, to the CNTIFIQUE, so this value of omega, how to convert it in of before?
Yeah. This has to be done with some economists, together with some economists, you know, because as I mentioned briefly during the presentation, that omega, that discount factor, could be a very complex. Actually, economists work with this omega. They try to, the more processes you bring in, the more complicated is omega. You know, the function with which you can capture that aspect, the socio-economic system. So could be job security, could be, you know, the legal system, the certainty of that if there is illegal fishing, that that person will be caught and brought to justice or whatever. Yeah. So that can be a very complicated in itself. Yeah. So all what we could do in this simple treatment is to say, okay, when omega is small or when omega is intermediate or when omega is high, to see what happens, right? Now it's to the economist to say, okay, omega high means, you know, could be mean many things. Depends also on the this is a general, you know, application, very general abstract application. You can apply this to a real case, and for example, the fishery system in Bur might be even a bit different. No, well, I don't think it's very different, but could be different than Ghana, for example. And therefore, you might think about, okay, how could be omega as a complex function for Senegal, and how could that be for Ghana or for Germany, right? Because I mean, otherwise it becomes a trivial thing. Otherwise, you put a quota, and that's it. I mean, that's what people do in Europe. Yeah, they put a quota, and then, but then you need to check every time who has the license, and when they come, did they fish below the quota, and so on and so forth. You know. So yes.
Sometimes if we put some kind of test
Mhm.
with this kind of question. So we can say
Mhm.
if you have, for example, a kind of value of food, so the system
Yeah.
will be have condemned.
Yeah.
So you need to integrate the value of
Yeah. Yes, of course. Okay, that would be the next obvious step. Yes, of course. Yeah. We haven't done it. We haven't gone that far, but that would be the obvious next step.
that's okay. Yeah. Thank you very much for the speech.
Thank you.
I appreciate it. But I have just one question about Omega. For me, the most important thing is the amount of resources available.
Yeah.
Because if there are competition between species or between stakeholders,
Yeah.
Omega is very, very large.
Yes. Exactly.
For example, if we can have a scenario also, if we have needs for food security,
Yeah.
for example,
Yeah.
this kind of problems we cannot specify or we cannot use users who have
Of course. Yeah.
the harvest business behavior.
Yeah. Of course.
I think so. It is
Yeah.
very complex for our country to control this kind
Yeah.
of parameters.
Yeah. Yeah. Of course.
Another thing is socially, what is the behavior of different actors and controlling also for economic issues.
Yes.
For example, traditional fisheries and industrial fisheries.
Yeah.
There is difference
Of course. Yeah.
about
Yeah.
economical interest. About some economic interest.
Mm.
Some users may do not have the
Mm.
same habit behavior.
Mm. Yeah.
About okay, some actors
Yeah.
may not have the same habit
Yeah.
behavior.
Yeah. 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 Of course. I mean, but that's. I mean, of course, you lose with this approach. You lose the individual by individual information. You lose that information. Of course, I agree with you. But you know, sometimes there are. I mean, this is one approach where you can get a broad understanding. Yeah. I mean, and of course, having done that, then you have to go into the details. Yeah? And in fact, actually, you know, that's the follow-up work we did. In the follow-up work we did, we developed a slightly different model, an agent-based model, not based on differential equation, but based on agents, yeah, and a more simulative type of context. And we developed it actually for the Senegalese artisanal fishery. And we created a situation in which we have some marine protected area, because nowadays, you know, I always tell these anecdotes. I was traveling with Akim Shooter, the guy I mentioned there. He's an economist working in my institute. We were traveling together in Central America, in Costa Rica. We went, he's an economist, he interviewed people, fishermen, and so on to try and understand the situation and so on. We went in Costa Rica there, beautiful place, a very old fishery village on the north. Oh, this is recorded, right? Oh, okay. I'll tell you this anecdote later. Okay, better I don't say that. Okay, so I tell you something else. Oops, I just okay. So what we did, we developed an agent-based model for the Senegalese artisanal fishery because everybody now says, oh, okay, the solution to protect the ecological resources is to create a marine protected area, close the ground, prevent people from going there. I hate this approach because if I was in those people's shoes, I would do whatever I could, to sustain the life of my family. Anything. Okay. So, and that's anecdote that I wanted to mention, but okay. Um, so we thought, okay, how about having a nation-based model, and then we see different type of cooperations among all the individual agents, right? And we see how cooperation, many different situations, could be better, right, than closing the areas, yeah. And then we also tested different configurations. If you're interested, I can forward you this paper. So there is a little bit more, right? This is like, let's look at the general concept. Let's see, right? But having done that, of course, if you want to really solve the clear case, you have to go either to implement an omega that is really detailed and so on, or look at the individuals and so on, because that's how fishery sciences nowadays address. Okay, but all fair points.
Thank you very much for the invitation. I have questions. The first one is in the beginning of the presentation, you showed the map with the geographical research interest.
Yeah.
And in this map, I see you have a deep interest for West Africa. My question is, if you have ongoing projects there,
Yeah.
yes,
I think so. Yes, yes, yes. There are not me personally at the moment. I had a project that has just ended last November, but there are other groups in my institute that have ongoing projects in Senegal. Not only Senegal, but Mauritania, Ghana, and so on.
okay. And the second one is what is the accuracy of the model?
What is the accuracy of the model? Oh,
And and the third one is could you adapt your model because I think with the general macroscopic scale. If you go to the small scale, you do integrate many other parameters.
yeah.
I guess no.
That's
And it will and also for this kind of case study, what would be the accuracy? Because I think if you go down, the accuracy will be also more high because you need to integrate with the
yeah, yeah.
yeah.
I mean, but this is the eternal dilemma in mathematical modeling. How complex you can go, how complex you want to go. I mean, more interested in very simple models, as simple as possible. I mean, for me, models are like geographical maps. You haven't seen and never seen a one-to-one scale geographical map. Doesn't make any sense. I mean, what does it mean? That a one-to-one scale of a geographical map means that you need to resolve all the single atoms in the environment, right? I mean, having such an extremely detailed model means mimicking nature, but nature is complex. We don't understand it. What's the point in creating a model that tries to mimic nature that's complex? So I think you gain some insight, some understanding by simplifying. And a 1 to 100,000 scale, yeah, you don't see everything, all the features of that geographic location, but still you can move from point A to point B with that map. And that for me is this, perhaps this is really 1 to 1 billionth type of scale, yeah, this approach. But it's still taking you somewhere. It's still giving you some indications. is telling you, okay, with climate change, social security, we need to look at that. And then we can look at that. We can look at social security, and go into the details. In that sense, of course, that's the eternal dilemma, how complex we can go. But then if you go that complex, there are so many parameters we cannot constrain, we don't know their value. Then we have lots of degree of freedom. So strike the right balance. That would be my message. And I tend to prefer simple things. I mean, yes, it has to be. It has to give you some insight, some understanding of the system. Otherwise, it's not a usable exercise. Yeah, I hope it was a little bit useful. Yes, yes, I do. Yes, 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 yes. There is a little bit of risk there because also decision makers should understand that we cannot create a perfect, you know, extremely high accurate resolution. I mean, suggestion, advice. There are risks, and we need to take such risks. I mean, doing something is better than simply just destroying our environment, right? Yes, I mean, but we simply can't do the perfect solution, the perfect advice for policymakers. Wow, guys, this is very interesting. So many interesting. Yes, of course. Yeah, yeah. I'm very happy. This is very stimulating discussion. Yeah. Mm. Mm. Yeah, I mean, one could adapt that model, but I mean, the model is very simple. I mean, perhaps, you know, you are more, going in the direction where, you have really a hydrodynamic model with transports and mixing and turbulence and so on and so forth. So this is a bit too simplistic, and it's only really capturing the broad ecological features. Also, the resource is growing logistically with a fixed current capacity. I mean, the only thing that is really changing there is the maximum growth rate of the resource, which is assumed to be a random walk around a fixed mean. So, I mean, I think this is a bit too simple for what you have in mind. What you have in mind calls for hydrodynamic modeling and coupled to a more sophisticated ecological model. Yeah. But that's the thing, I mean, that's the problem. Because of these problems about complexity and many parameters and so on, I always had the feeling that either you have a very highly sophisticated physical model and a very simplified ecological component, and what is the social part? Not even there, right? And then either you have the ecologists who have the very sophisticated, highly ecological model, and then they don't care about, they kind of, leave aside all the socioeconomic. And then you have the economists that have all the very complex socioeconomic system and so on, and then the ecology is just a parameter. So when we were developing that approach, I mean, how can we put the ecological resource and the socioeconomic aspects on the same level and still keep it simple? So that's mainly something different. Yeah. Yeah. Yes. 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 Yes, I mean here, I mean what is the sediment, the coastal resource is a source of variability for the fish, right? And basically we capture that with the random walk, basically, yeah. But of course, perhaps that could be coupled. I mean, perhaps your model could give, some sort of variability in the growth rate of the resource, and then in that way it can be captured. Yeah, perhaps that could be a direction. Yeah.
Thank you a lot for your guys' presentation. We say you again welcome in Amadou Mahtar
Thank you.
It is a wonderful presentation that describes the behavior of the owl. Me, I'm curious. Now, in the beginning of your presentation, you have described for your academic institution 20 group concepts.
Yeah.
I want to say, I want now if for the group, among the groups are these some groups for chemists.
Yeah.
And
there are.
how to facilitate the partnership.
Yeah.
With the group
Yeah.
of chemistry.
Yeah. So yeah.
Now I read in your presentation a sentence or question. What is what is the event secret for success? I want now your answer for this question. For me, the partnership can contribute to the success for women. For you, what is your answer? Thank you very much.
Okay. First thing, yes, there are chemists in our institute, and more specifically, biogeochemists. They are in the biogeochemistry in the geology department. I myself am also interested in biogeochemical modeling. I'm interested in marine carbon chemistry, how emission of how burning of fossil fuels or emission of CO2 create ocean acidification. That's the other side of the coin. Yeah, on one side we have greenhouse effect, global warming. On the other side we have ocean acidification because the CO2 diffuses into the ocean, and by diffusing into the ocean makes the water more acidic. It lowers the pH of the ocean. And I'm interested in understanding what is the impact of ocean acidification on organisms. For example, organisms that calcify, that produces shells, calcium carbonate shells. For example, coral reefs. A big research line in my research is towards coral reefs, which is an iconic ecosystem of the tropics. So the center, one of the center of our institute research. Okay, so yes, there are, and we can discuss. This is my first visit, and as I said, I hope will be the first of many. And later, whoever is interested, we can discuss about grant opportunities, grant overview, framework for cooperation, and so on. We have that in mind with Professor Faye already. So the second thing, what is the secret of success? I mean, that is really sarcastic. I mean, I call it success, but what I mean is, we are destroying our environment, yeah, and we are doing very little for that. Every one of us is not willing to give up something. Every one of us is discounting our own future. I mean, I know, and I totally understand it. I'm saying this from a very privileged position. Being an average European guy, I'm saying this from a very privileged position because Europe and other, Western countries or highly developed countries had done their share in emissions and in pollution and so on and so forth. And now, there are other countries who obviously claim, but to develop, we need to emit, we need to use the resources and so on. So how do we solve this dilemma? So it's not success, obviously. We have not learned in using our environment, and The secret, it's not the secret of the success. I mean, for me, it's just a provocation, of course, right? I just want to start the whole thing with a provocation and in order to attract the attention. But what that really means is how we come, and I also mentioned it, how we come to dominate among the all possible species, how we come to dominate, to be the dominating species on this planet. Yeah, as I said, 60,000, 70,000 years ago, we were completely insignificant. You know, turtles were more important than us. You know, only 60, 70,000 years ago, we were completely insignificant. At some point, something happened that gave us, and many anthropologists, they believe that this ability to combine flexible, highly flexible cooperation in very large numbers. That's why I got interested in cooperation and how cooperation can be described in a fishery system and so on. Right? That's just the storyline. I don't know what is the secret of us being dominating. We are particularly bad, perhaps. I mean, other organisms there seems to be able to live in a better way with their environment. I don't know, more in a better harmony with their environment. Somehow we discount. I think that's a big problem. We discount our future. Yeah, that's the thing. I mean, we need to find mutually beneficial solutions. Between Europe, between Africa, between where we can find a win-win situation. It's difficult. It's our dilemma. But if we want to have a future, and if we want to leave a planet that is livable to our children and grandchildren, we need to sit down and try to solve the mess we are creating. It, it's a general situation. Yes, yes, yes. This is a very general, model. Of course, it's fairly abstract. It's not even specified whether it's Senegal or Europe or anything. It's just a general situation. Of course, applying this model to a specific case would mean try to make that omega a little bit more specific, not just one value, one fixed parameter, but make it more specific, right? To the specific case. So for Senegal, that omega will be a particular function, complicated function, and from somewhere else in Europe will be different. That's how you could apply that model to different places by specifying omega for that specific place. Because that omega means governance, means how the people behave in that system and so on. Yeah, but that's the critical aspect. Yeah. Yes. My personal, yes. Yes, of course. Mhm. Yes. Yeah. Mhm. Of course. Yeah, of course. I have I have something to say about that, but that is the second part when yeah. So we can discuss this in the second part. There is a second part about cooperation and about funding frameworks and so on. What was this? Yeah. Yeah. We did, but now that you are so much, we did something else actually. So the idea was to gather data, to try and understand the cooperation. Basically we team up with some colleagues from Senegal, in various institutions in Israel. We developed a tool. Actually, if you're interested, it's freely available, so we made it open access so that anybody can. Okay, let me go in the appendix. We developed a tool, an app. Okay, an app. So there is a server in Germany, in my institute, and on that server there is a model, a resource dynamic model. And then the app can be installed on pad or telephone, okay, and people can play. That's the screen you get from the app. I'm not sure if you can see, but one person will see this thing level, and that person can harvest from that resource through this or pad, and you can decide an effort here with this bar, which is a typical case in a fishery, right? In a fishery, you have to decide how much effort you want to put into your effort, into your fishing. I mean, effort means how much money I invest, how many pirogues I want to buy, how many fishermen I want to bring with me, and so on. The more you pay, the higher your effort. Of course, this means that you have to get more fish to be able to repay and have profit from that situation. So that was an economic experiment. This is done in many resource economics studies, and um, we did some work. So basically, you collect people in a room, you give them this thing, and you let them play. And then in economics, for these games to be valid, you need to actually pay the people who have, based on how much they have gained. That is the incentive for people to play seriously that game. Yeah. And like that, then you have different treatments during this experiment. You can say people that are playing do not talk to each other. Everyone on his own. And you see what happens, how the resource is managed. Then you have another treatment where you say you can communicate with each other and look at each other activities and decide what you want to do. When nobody talks, everybody tries to take as much as possible because it's easy, right? And you know that if you earn a lot, then you are paid. You pay in euros. I mean, these people at the end of the game. But obviously, everything collapses immediately. Nobody gains anything, right? Then you run it again. They can communicate. Okay. So, too much, reduce, so that everybody can. Right? So you have communication, no communication, punishment. If there are free riders, people can decide. They can check one another. They can monitor one another, and they can decide punishment in terms of he gets less money at the end of the game. So that's one way to gather data about human behavior, cooperation behavior, and then to encode those data into the. And so we've been produced that app, and we have published, and the app is free, so anybody can do experiments with that. You could do these experiments with students. We tried to do with fishermen in Bur, but it was really complicated because most of the fishermen, the French was fairly poor, and they could not understand the instructions, which were translated from English to French and from French to Wolof. And these experiments had to be highly controlled, otherwise they're not valid. So we tried a couple of times, but we did not succeed in the end. And so we did some experiments with normal people and with some, understanding of the language and so on. And we published some results, but it's not really with fishermen. So at some point, I wish we could do that with fishermen and so on, but we haven't got that far. So that's one way of collecting data with colleagues from Senegal and so on. And of course, there are other type of studies. I mean, I also get interested in different things. For example, one topic I'm very interested nowadays is about conflict emerging from resource scarcity, and conflict that can even, become violent conflicts, And there are such situations in Senegal, for example, and so on, right? That you can. There are several conflicts, but one classic, obvious conflict is between artisanal fishery and industrial fishery. There is a conflict there. And so I'm interested in trying to model these things nowadays. So, I tend to jump from one topic to another, so and leave things behind and so on. But, we've done some work also in the data as collection part. Hmm. 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 How? Mm-hmm. 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 The harvest rate, yeah, is varying with time, yeah, but it's optimized, right? That follows this adaptive dynamics approach. So the harvest rate moves in the direction that maximizes fitness. So it means that if the resource is getting low, the fitness is to get more and more of that resource that is going down. And so the harvest becomes more aggressive. Yeah. 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 Yeah, that's there. Yeah. Yeah, I mean, that's a yes, that's a partial derivative because the fitness function depends on many things. Of course, right? I mean, like that's the fitness function depends on many. Depends on the resource, which is changing over time. Depends on many other things, right? So it's a partial derivative because you only derivate the fitness function with respect to the trait. Sometimes it's very simple. You can do it analytically, plug it that there, and then solve it numerically with time. But sometimes you have to solve it numerically. Ah, sorry. In this particular, no, but you can do it analytically. Well, actually not, because there is X also in K. No, we do it with the no, with the Mathematica or something, right? So we do the partial derivative of f with Mathematica with one of these, and then we plug that df dx into that equation, the result that we obtain. Is that your question? Sorry, perhaps I didn't understand. Yeah. Okay. Yeah. Okay. Thank you. Yeah. Do I still need the things, or I can remove it, or I can take it off, right? Okay.